Hi everybody. On behalf of the Second International Network of Biomaterials and Engineering Science, I'd like to welcome you today. I am Assia Najm, a PhD student at University Hassan II of Casablanca. My research interests are software effort estimation based on machine learning methods. As you know, today I'll be discussing the Optainet-based technique for SVR feature selection and parameters optimization for software cost prediction. My presentation this morning is divided into 6 main sections. The first, introduction; second, previous work; third, the proposed model; fourth, empirical design; fifth, results and discussion; and then finally the conclusion. So to explain the motivations about our motivations about this study, we start by making a simple definition about software cost prediction, which is a crucial element for a project's success because it helps the project managers to efficiently estimate the needed effort for any projects. And there exist in the literature many machine learning methods like artificial neural networks, vector regression, decision trees, and many others. However, many studies confirm that accurate estimations depend greatly on dataset characteristics like the presence of outliers, the dataset size, and the presence of missing values, and also on the on hyperparameter optimization and on the proper input feature selections that impact highly the accuracy of software cost prediction models. So in this study, we use the SVR model and we make we enhance its performance through the use of the proper feature selection and parameter optimization. We note that during this study, FS is used for feature selection and PO is used for parameter optimization. In this paper or in this study, we propose an enhanced model using SVR and the Optainet algorithm. The Optainet is used at the same time for one, selecting the best set of features, and second, for tuning the parameters of the SVR model. Principally, the feature selection preprocessing step will make the data purer by removing unimportant features, while the parameter optimization step will find the best configuration that enhances the performance of the used SDCP model. We note in the study that the used approach is denoted as SVR Optainet with feature selection and parameter optimization. Concerning the previous work, from this section we intend to present a summary of some identified studies that investigate the use of the SVR for software cost prediction. We start by Oliveira, who investigated the use of the grid search technique in optimizing the parameter of two SVR models, the SVR with RBF and the SVR with linear kernel. The result shows that SVR performs better than linear and RBFN's regressors. The experimentation was made using only one dataset, the NASA dataset, and we note that no feature selection method was employed. Besides, the SVR model was also investigated by Braga et al. And Oliveira. They proposed the use of the genetic algorithm for both feature selection and parameter optimization. They proposed a binary chromosome that represents the suggested hyperparameters and the selected features. Empirical experimentation shows that the accuracy of SVM is enhanced using the genetic algorithm-based method, and it outperforms the bagged M5P and the bagged MLP. In the third work, which is made by Novitsari et al., the authors proposed a PSO-based approach for feature selection and parameter optimization of the SVR model. Nevertheless, this paper made the evaluation using only one dataset, which is the Dataset datasets. Also, the authors didn't employ the commonly used criteria in software cost prediction. Concerning the Corazza papers, the authors also investigate the use of the SVR model for estimating the cost of web projects over the Takatuku datasets. The results confirm that SVR is a promising technique thanks to its better performance regarding other software cost prediction model. They claimed that it is suitable for cross-company datasets through its corners and parameter settings. Concerning the last work made by Corazza, the authors in this paper also proposed an improved SVR model based on the table search method to tune the SVR parameters. The experimentation was performed using Takatuku and Promise repository datasets. The main finding is that the SVR using table search achieves a great improvement compared to CBR and stepwise regression. In order to explain our proposed model, the Optainet-based SVR model, we start by making an overview of the SVR technique. The super vector machine is an encouraging machine learning model that has offered valuable results in both classification and regression problems. The SVM approach has several attractive features like the sparse way of presenting solution, good ability of generalization, besides the capacity of avoiding local minimum thanks to the structural risk minimization concepts. In this present study, we used the epsilon SVR thanks to its ability, the epsilon SVR with RBF kernels thanks to its ability to generate good estimates. The hyperparameter of the SVR with of the SVR is the regularization parameter, the deviation, and the current parameter. In order to build an accurate SVR model, it requires the selection of optimal hyperparameter values. And there exist many optimization methods like genetic algorithm, grid search, particle swarm optimization, and Optainet, and others, and many others. In this study, we are interested in using the Optainet method, which means optimal artificial immune network. To explain the Optainet method, it is inspired from the biological domain and exactly from the artificial immune network model, which was introduced firstly by De Castro and Zebin. It is a graph composed of nodes and edges. It is essentially based on immune system theory, where the immune system generates a great number of antibodies or attempts to provide the best suited antibodies for attacking antigens. The modelization of this phenomenon corresponds to a function optimization process. So the Optainet method has many attractive features like the inclusion of stopping criteria, ability to check and maintain various optimal solutions, the capability of dynamic adjustment of the population size, and the capacity to exploit and explore the whole space of search. We adopt the next terminology to explain the Optainet algorithm. The cells in the network is composed of population values. Cells fitness stands for the objective function value using a particular network cell. Cells affinities represent the value of Euclidean distance that exists between two cells. Cloning is producing a replication of original cells, and mutation stands for that the original copies will be mutated to be different from their parents. Next, we explain our proposed model. This figure is represent the design of our proposed model. Firstly, we proceed to the data pre-processing phase, where we normalize all the available data in the range between 0 and 1 to straighten the accuracy of the regressor. After that, we make a 30% holdout method, cross-validation method, to split the dataset into two main sets, the training sets and the testing sets. After that, the main steps of the Optainet algorithm were performed: the cloning, mutation, fitness evaluation, affinity measurements, and network separation. And the output of this algorithm is finding the best solution with feature selection and parameter optimization. Concerning our empirical design, we start by the dataset description. We used the 7 datasets, which are the Albrecht, Kokomo, China, Desarnais, Icebag, Kimmerer, and Miyazaki. This table explains the main descriptive statistics of these datasets. Next, we use the three accuracy criteria, which are the mean magnitude of relative error, the breadth, and the mean of the magnitude of relative error. Concerning the validation method, we use 30% holdout method, which uses 70% of the dataset for learning the model and 30% of available data as test sets. This method is advantageous because the model performs prediction on unseen data samples and therefore produces less based cost prediction. So now we present the results of the comparison between our model and other models, which are mainly the SVR using Optainet parameter with parameter optimization without feature selection, the SVR BFO, which means the SVR using backward feature elimination, and SVR Borota using the Borota method, and SVR without feature selections. We observed from this table the values of breadth over all datasets, where our method outperforms all other SVR configuration in terms of breadth 25%. Besides, we mentioned that the SVR using Optainet just for parameter optimization came second thanks to its best spread in 5 out of 7 datasets. So the table 3 and table 4 presents also the results of comparison between our model and the other models in terms of errors of MDMRE errors and MMRE errors. According to MMRE and MDMRE results, we notice that our method also outperforms the majority of other techniques over all used datasets, where the minimal values of errors were obtained using China datasets, while maximal values are obtained using Kokomo datasets. So concerning the conclusion, our model was compared to 4 other SVR models, the optimized SVR without feature selection, the SVR using backward feature elimination, and SVR using Borota feature selection, and SVR without feature selection. The overall evaluation was performed using 13% holdout method. And the result shows that our proposed method outperforms all the 4 SVR configuration based on all datasets in terms of 3 used criteria, which are the MDMRE, MMRE, and pre-25%. Concerning our future work, it would be interesting to generalize the predominance of our proposed model by comparing it to other non-SVR models using leave-on-out cross-validation method. And thank you for your attention.